Good evening, sir.
Hello, Pratham. I'm audible.
Yes, sir.
So I'm just sharing my screen. So, which was the last topic we covered? I think we covered okay a dipole moment. Yeah, we covered the dipole moment on the equilateral position. Okay? So today we'll be covering dipole moment at any random given angle theta. Also the energy stored in a dipole moment. Okay, these
Okay.
two topics which we have to cover in today's class. Alright, so when we'll be covering that, let's make it clear. Dipole, yeah, electric field due to dipole at any random angle theta. Electric field due to short dipole. Okay? Why I'm calling short dipole, I'll explain within a minute. Due to a short dipole. Yeah. So this is, I think, now you can see the screen. You
Yes,
lecture
sir.
part. Okay, dipole moment at some general point. Short dipole at some general point. Okay?
Okay.
What it actually meant is earlier we discussed if I have some dipole moment, let's say q and minus q. Earlier we discussed two cases. If your how to calculate electric field on this equatorial line, equatorial, okay, and this axial, okay. Now our point, sorry, and now our point of discussion is to calculate electric field intensity at a very random point. For example, this. Then how we can calculate? All right.
Okay.
So let's make a very short dipole q and minus q. Calling it a short dipole because the distance we have to assume it a very small. Okay.
Okay.
So in this case, what's going to happen? Let's say this is the connection. Okay, this is point center point. We can say so. This is length L. Now you know what is the direction of dipole moment. So I can say this is the direction of dipole moment, negative to positive side.
Yes.
So I can write it as P. Now I want to calculate dipole moment at this angle. So what I should do is I know one thing. This is my dipole moment, is it? So I can resolve it into the two vectors because it's a vector quantity. So you know the vector quantity can be resolved into two. So if this is theta, this will also be theta. Understood?
Yes.
So if this can be resolved into two direction, one in this as a p, okay, maybe something we are not sure, and another one is this. Okay, fine, fine. It will be in this direction. One is this direction, one in this direction. Clear? So this will be your p of cos theta, and this will be a p of sine theta. Okay, so I hope
Okay.
it is clear for you now.
Yes.
Some in some books you will see that they have taken the angle towards the positive side. For example, if you take it towards the positive side, it will look like this. Positive. This is the center point. It is going like this. So you know this is the dipole moment. So dipole moment will resolve like this. This is theta, so it will go as p of whatever it is cos theta, and downside it will be p of sin theta. Okay. So you don't have to take care of like which is correct or not. At the end of the day, whatever theta you are choosing, it will do your work. Clear?
Okay.
Okay. So if you see carefully, for this dipole, isn't it this position is an axial position
For which?
for this dipole, because I have resolved this p dipole into two, like this and like this. Okay, so this is your
Yes.
p sine theta, and this is p cos theta. Now you can assume that you have two different dipoles. Okay, so due to this, it will be act as an axial position for it, and this will,
Yes.
because it's a perpendicular to this, it will act as an equatorial. Right,
Yes.
this is dipole, you have equatorial. So make sense?
Yes.
All right, so we'll calculate it into the two bases. First is electric field due to the perpendicular dipole. What it will be? This is the dipole moment, and this is the point where you want to calculate electric field. So what was the formula? That is negative of kp divided by x square. Clear?
Yes.
So if you see carefully, this is the distance. Okay, so yeah, this is what it looks like. Okay, this is the negative. So basically, due to this dipole portion, your electric field will be going into this direction, opposite to the direction of dipole, because negative is there. Cube was there, I think. Okay, electric field due to
Sir,
this is
that is
yeah
for
this
perpendicular, right?
yeah this is for the perpendicular and distal part. Okay, for parallel you can write it as 2kp divided by x cube.
X
Is
cube.
it clear?
Yes.
Okay, so you see this is a parallel position. Okay, what will the electric field at this point? It is in the direction of this dipole. You can see this. Understood?
Yes.
So, what will be the final direction of electric field? If I ask you what is the final, so it will be coming somewhere around this. So you just have to do one thing: E net, add E net, do E net. If you do E net, what you are going to get is E perpendicular plus E parallel. Put the values. When you put the values, you will be getting take Kp outside. Okay, so you will left with only what is it, minus 1 by x cube plus 2 by x cube. So what you got finally? Something like kp divided by x cube. This is the final value you are having if you do the simple raw vector addition. Clear?
Yes, sir.
Okay, so this is the dipole direction. All right, so this is what you have got as your whatever I told, direction of electric field. Okay, this is your final summation of both cases. Clear?
Okay, sir.
Any doubt? Just take a look at this.
No, sir.
No, okay. If I ask you what is the magnitude, so what will you say?
KP by X cube.
Kp by x cube. Okay. What do you think? Whatever this is, whatever we have done here, is it correct or not?
We haven't used the components or anything.
Exactly. We haven't used the components, right? So basically, when I was talking about the perpendicular portion, I mean to say this. So here dipole not was not only dipole; it was sine theta. Okay. Here what
Okay.
it was cos of theta. Clear? So you
Yes,
have
sir.
to take them into consideration also. So just we can remove it for a while. So what you are going to get is just do the magnitude first. Okay, let's calculate the E net magnitude. So when you do this, the square of this, the square of it, it will come out as how much? 1, okay, kp by x cube we can take outside of the under root. The thing only inside is sine square theta plus 1 plus 4 of cos cube theta, cos square theta. Okay, moreover, if you resolve it out, it will comes out as 1 plus cos 3 cos square theta under root kp divided by x cube. Is that clear?
Yes.
Okay, this is the magnitude. It doesn't tell anything about the direction. So for the direction, how you can solve it out? Again, let's put the direction thing. All right. So if you see, I will just remove the magnitude thing. Okay, I won't get into the magnitude part. What is direction over here? If you see, this is my direction minus sine theta plus cos theta. Is it?
Yes.
Just a second. So what you are finally going to get as in the form of direction, that is tan theta. Okay. Basically, we have to solve this one, right? Oh, all right. Let me just remove this part. You know what is the value of this one? This is the E perpendicular, right? And this is the E of parallel piece. Okay. So one more thing, in which direction we have to get the total net direction of electric field? It can be taken with respect to this line. Yes. We can call it some angle phi.
Okay.
So what is the value of this phi? It is nothing but, if I ask you what is the value of this phi, so this is nothing but tan phi, which is equals to E perpendicular divided by E parallel. If you put out the value, you will be getting something like 1 by 2 tan of theta. Understood? This is what you are going to get.
The negative.
Negative, very okay. Negative we can cancel out because it's not that important part for us.
Okay.
Okay, the theta will take care of it itself. So that's why we are not
Okay.
including the negative part. Understood?
Yes.
Oh, so ENET not important. Can directly put tan phi equals to how much? 1 by 2 of sine tan of theta. Remember this phi is with respect to this. Okay, the line.
Okay.
So I think by this we have covered this portion also, and we can move to the. Okay, I have one problem, and I'll give you this problem. Okay, you can try it as a homework part. Just a second, I'll face the problem. So this is the problem you have to solve with respect to this topic. Okay. Apart from this, yeah, let's talk about what is the net force on a dipole, in a dipole in non-uniform electric field. Okay.
Okay.
So what is it? Net force on a dipole in non-uniform electric field. Okay. Yeah. So if I just assume I have a non-uniform electric field, it means the magnitude is varying, right?
Yes.
If I have a charge over here, charge over here, let's say this is q, this is minus q. So I know one thing, even though they are what I can say, they are what kind of thing? They are bounded because the distance is very small, and they are opposite charges, and their short dipole means to say they are bounded thing with each other. Okay, something like this. But this, if I'm assuming that this is a positive charge, this is negative charge, something positive charge might be here, then this is because you have electric field in this direction. So force on this will be in this direction, is it? On this
Yes.
dipole, force on this one will be towards this. So what
Okay.
is the net force that we have to think of it? So
Okay.
if I tell you what is the force, force is nothing but, let's talk about the force on bigger q. So force on q is nothing but E, E into q, right? And if I
Yeah.
ask you what is force on minus q, if I say it is a non-uniform but it is varying, let's say from here to here, the difference in electric field is delta E. So can I say the electric field is nothing but E plus delta E times of this? Can I say this part?
So can you repeat?
I'm saying that at this point, look, at this point in electric field, I had electric field E, and I
Okay.
told you that it is varying. So I can say that when you move to this point, the electric field will not be E, it will be something delta X, delta E.
Yes.
It may be positive, it
Okay.
may be negative, right? So can I write this, whatever I have
Yes.
written on this? Okay. Also, if I calculate F net, what it will be? You can do whatever you want, e1 eq minus e plus delta q and whatever. Okay, why I'm saying this, one charge is negative, one charge is positive, so you are, if you add both of them, you are going to get this one. Understood this part?
Yes.
So if you solve it out, what you are going to get, delta e by q, or better you will write it as q delta e. Understood?
Yes.
All right. Okay, we have made any mistake or something. Okay, that's fine. Okay. So this is for now Fnet. Is it complete Fnet? So my answer is no. Let's do one thing. We try to convert it into the form of dipole. So if I do one thing, Q delta E divided by delta X and delta X. So what it becomes? What it becomes?
Q delta E.
Yeah, let's go further. Fnet equals to
Sure.
Q delta X delta E divided by delta X. So if you see carefully, when I told you this difference, so this delta is basically the difference of this part, and this is nothing but the distance between 2 points. So can I say this is the difference between 2 points?
Yes.
Okay, and charge multiplied by the distance of the dipole, it will give me nothing but the dipole moment.
Yes.
So I can replace this thing with the dipole moment, right? So
Yes.
what I got Fnet? Fnet is nothing but dipole moment multiply delta E divided by delta X. Okay, this is what it is.
Okay.
Clear? In the
Yeah.
magnitude, basically, just remove the vector part, put that same into the magnitude. Understood
Okay.
now?
Yes, sir.
Oh, and yeah, you can just, if you solve it out, solve in a proper vector form, so you will get the answer as a correct thing. Okay. So this is what it is about. Net force on a dipole in case of non-uniform electric field. Now, if I ask you, the electric field is uniform, then what you will do? If my electric field is uniform, then this portion will come out to be zero. So I can say F net, make another case. If electric field is uniform, then what we can do is very simple idea. Then delta E by delta X will come up as zero, which results in F net to be zero. Make sense?
Yes.
Fine. So, all right. So your task is to find the force on a small electric dipole of a dipole moment P due to a point charge Q which is placed at a distance R. Okay, this is a question. You can solve it in the right now. So,
So you आप लिख रहे हो या फिर
no, no, मैं नहीं लिख रहा हूँ. Okay, I'm not
okay?
writing it over here.
Can you
You can
just
just,
repeat?
okay, you just have to calculate the force on a small electric dipole. Okay, having dipole moment P due to point charge Q. Okay, leave it. I'll just write it over here. If you understand, you can start solving the problem.
Yes,
Tomorrow,
sir.
I will write here also. Calculate force on dipole of dipole moment P due to charge q at distance r. Okay, this if you solve it out now, it will give you a result. Basically, it will give you a result of interaction between a dipole and a normal charge.
Okay.
And after this, we have last topic left, that is dipole in a uniform electric field. With respect to this chapter, after this, we will move to the basically a part of this chapter itself, that is potential difference and capacitance. Okay.
Okay.
Alright, so I think 7 lectures needed for this portion. For potential, I think 7 lectures also required. Then we will end this chapter by 1 or 2 class of problem solving.
So can you scroll a bit up?
Um,
That's it.
is it fine?
Yes, yes. Enough. Oh, okay, sir, done.
Then okay. So what's your answer?
So it's going out to be 2pkq by x cube.
2pkq by x cube. That's fine. Okay. Okay. How did you solve this?
So first I use the like the formula for first I use the formula for dipole, that is f into dipole into f is equal to dipole into dx de by dx. Then
Okay.
e is equal to kq by x square. Then
Clear.
then I differentiated with respect of x because we had to find the de by dx.
Exactly. Exactly.
So
So this is
then after differentiation I
that's
got 2kq by x cube.
all right. I will tell you one more method. Maybe if you find this one easy or like short method. If I place a random dipole P, okay. So due to this dipole, there will be electric field at this point.
Yes.
Okay. Let's say my charge Q is placed here itself. Okay. So now tell me what is electric field at this point if the point is at x distance.
Yes.
Will it be the okay? What will be this? What will be the value of electric field in this case?
Electric field.
Intensity, whatever
Uh,
we have studied before now.
yes,
These
yes.
things, if you could remember,
Two,
okay, assume it to be the axial position,
okay, yeah. Then 2kp by r cube.
2 kp by r cube, or you can say x cube. Is it
X cube, yes.
okay? So if I ask you what is the force on this charge q, so you can say, sir, force is nothing but E cube, which comes out 2 k. PQ divided by X. But I know one thing, that electrostatic follows the third law of motion, meaning to say, whatever the force this is going to apply on this, the same force this is going to apply on this. Is it?
Yes.
So can I
Yes.
say the force applied by the Q will also be the 2kpq by x cube.
Yes.
Got the point?
Yes. Yes.
All right. So you can apply this method where like maybe one is force from one to another other is given, and you have to calculate this to this. You can just equate with this because it follows the third law of motion.
Okay.
Just remove it out. Okay. So the last part of this topic, today's class, dipole moment on uniform electric field. Dipole moment in a uniform electric field. FIELD. Okay. So, as per the question, you can see it is a uniform electric field. One thing you know, if I put my dipole in the uniform electric field, what will happen? The net force is going to be zero, is it? Hello, Pratham. Am I audible?
Sorry, sorry, I was muted. Yes, sir, it will
Okay.
be zero.
Yeah, it will be zero, right?
Yes.
Okay. Mean to say, if I place my charge like this, because one force maybe one force in this direction, like okay, one force in this direction, one force in this direction, they will get cancelled, is it? So I can say F net is going to be zero. Is that clear?
Yes, sir.
Okay, let's remove this place. Now tell me what will be happen if I have something like this. Force is in this direction because force is will be same, right? Magnitude will be same. So now tell me what will happen.
Uh,
Let's say this is the center point. So don't you think about this center point there will be torque on it?
oh, yes.
Yeah. Okay. So
Yes.
let's say this is L. This is also L. So if I ask you what is the torque, so what will be the net torque?
I forgot the formula.
Okay. So net torque will be basically the force. Basically, what is net torque? Net torque is nothing but the distance, whatever the distance you have, and multiplied by what?
Um,
Okay. The force multiplied by the distance. Okay. R cross F. It happens is R
yes.
cross F.
R
Okay.
cross
What
F.
is R here? The distance. So that is I can say 2L. Okay. Let's not write 2L and all. Make it simple. Make it very simple by keeping it L. Okay.
Okay.
So this is L length overall. So remove it L cross F. If you remove, if you put into the like scalar quantity, like make it scalar, what you are going to get? R F sine theta. Clear?
Okay.
Because okay. So what is R here? R is the distance. So L, what is force? F. F is nothing but Q multiplied by electric field. What is sine theta? You have to just keep it like this. What is this? P, dipole moment, electric field, and sine theta. What you got in final torque? Torque comes out to be P cross E. I just remove the sine theta. Understood this part?
Okay. Yes.
You can, okay, instead of going through this step, you can start from here itself. Put the value of F. So if you do this, you'll be getting E multiplied by Q. Take this portion as a single portion, basically Q R cross F, because it's a scalar. So this scalar can go to here also, go with here also. Okay. So now this becomes P cross. Understood? Whatever we did in the three step. Till now, any doubt you have?
No, sir.
Okay, this is what we have calculated the torque. So what it means is the net force. Even now the net force is zero. Now what happens if you see? uh, actually I have made this a little bit different. Okay, let's calculate the energy. If you see, I'll make some cases. For example, this is electric field, this is electric field, this is electric field, this is okay. If my positive charge is here, negative charge is here, what do you think? What will happen? A very simple idea is there. This is a positive, it will go away. It will go away with the electric field. Mean to say in this direction. It will go this way. So it means there will be torque and it will rotate, right?
Yes.
So it is going to rotate, it means it must have some energy, U. It
Yes.
must have positive energy, then only it can move, right? Okay,
Yes.
let's
Yes.
take another case. Um, okay, let's say it is like this. What happens? Still now it will move like this. Okay, now tell me what will happen in this case. Electric field in this way, electric field in this way.
Cancel.
No, it won't move, right? Can I say it has zero energy?
Yes.
Okay, that's fine. But if I ask you, if I just give a very small push or make it like this and leave it, what do you think? What will happen? It will again reach its
Torque.
original position, right? It will again, due to like, it will get a torque and it will come back to its position. Is that
Yes.
clear? So can I say this is nothing but its bounded state? This configuration is its bounded configuration, mean to say from here, even if you give it a small pull, push, move it, it will again go back to its position.
Yes.
So I can say that it's the most stable position. Is that clear?
Yes, sir.
If it is the most stable condition, its energy will going to be negative. Okay, basically the minimum energy it will be having. So let's assume it to be the
Okay.
negative. Clear? So
Yes.
this is a positive energy, mean to say it is unstable condition. It is negative, it is one of the stable condition. Okay, maybe it is more like, what I can say, it is most stable or not. It's this, we have to check it out. All right. Now, if this is the condition, what will happen? Right now, the torque is zero. That is fine. But even if I give a small push, it will go into this condition, something like this. Get torque, change its position, like this.
Okay. Yes.
So can I say it is stable condition, but it is not in proper equilibrium? So can I say like this is equilibrium condition? Okay, it is not moving anymore. So can I say it is unstable equilibrium?
Yes.
All right. So for we have checked many cases. Okay.
Can you
So
repeat, sir?
yeah, no. What I'm saying, we have checked out many cases. One is this case, unstable. Another was this case. It was an equilibrium, but it was what kind of equilibrium? It is unstable equilibrium.
Yes.
This case, stable equilibrium. Clear?
Yeah.
And electric field was going like this.
Yes.
Direction of electric field. Okay. So now calculate the energy.
Energy in all three cases.
Yeah, energy. Okay, wait. I think we should not calculate the energy also, because energy is in the next chapter. Okay, I will just calculate it, and in the next chapter we will do a recap of it. Clear?
Okay.
One more thing, we will get a general formula. Okay, when we solve that general formula, you will get the answer for all these three cases. Okay,
Okay.
just like this, the formula we have calculated, right? Now it is applicable for all three cases. If you see carefully this formula, what is the angle between your dipole and this? It is nothing but this sine theta is nothing but the angle between dipole and this, right? So you can see it is 90 degree. It
90.
means it is maximum. You can see here you
Yeah.
have a maximum torque. In this case, what is the angle? This is one angle, this is one angle.
Zero.
180 degree
180.
comes out zero. Here also
Yes.
the torque zero comes out zero.
Zero.
Clear?
Yes.
So one formula applicable for all these. You can see here also, when we I calculated for the non-uniform, I didn't made any other case. First I calculated non-uniform. From there we got into the uniform directly. Yeah. So
Yes.
work or energy of a dipole. uniform and uniform. Alright. So, if this was the case, let's say this is a stable condition. Okay, my dipole was in this condition situation, positive, negative. What I did is, I took this charge from this angle. Let's say yeah, electric field angle, right? So this was this was at this theta one. What I did is I took it from this and place it to this angle. Mean to say something like this. Understood my point?
Okay. Yes.
What I did, I just changed it. So whatever energy I have to put to change its position, that energy is going to stored in it. Can I say this?
Mm.
So what is the
Yes.
work done I have done? Work is done is basically the torque. What torque I had to apply? Torque multiplied by what is the position? By what position I have changed it? So in case of when torque is there, I can write it as theta. Is it?
Theta. Yes.
Okay. So what is the torque? The P cross E multiplied by the what is that? Theta. I can say it angle. So it will become how much it is. Mm, okay, torque into theta form it will come out, right? But our answer will not be in the theta form. Let's not write it, do it in this way. Let's calculate it in the form of force, okay?
Okay.
Because theta formation will not be helpful for us in solving the problem. Let's say this is the condition, okay? This is the force on it, and this is the force on it. This is the length. Now what I want to do is, I have this is the current angle theta. You can assume it to be the theta, okay?
Okay.
The dipole is like this and this. Not this. I think it is not a good option. It will seems better. Okay, this is your angle theta with respect to dipole and your electric field. Okay, this is the angle between your dipole and this. I'm removing it for now. So this is the force on it. Now what I'm doing is I will just rotate it by more angle and I will take it to here. Let's say this is theta 2. Clear?
Okay.
So when this was the force, to move it from here to here, I also had to apply this much force. Is it?
Yes.
So what work that I did? I did force into distance. This distance I moved on. Is it clear?
Yes.
Okay, how much distance I went? This was the length L. Is it
Yes.
okay? And if you see what is this angle, this is basically L cos theta.
Okay.
Basically, two components are there, right? If this is
Yes.
like this, I am interested to calculate this because this is the distance it has calculated. Okay, and this was the
Okay.
theta. So if you do L cos theta, you will be getting this component. If you do L sin theta, you will get this component. To get the
Yes.
torque, we needed the perpendicular part, so we did L sin theta. Here we need L cos theta. So
Okay.
my R, because work done is nothing but F dot R. Okay, so if you just re-clear it, you will be getting remove the vector portion. We are into scalar right now. So F multiplied by what? L sin theta, L cos theta. Is that clear?
Yes.
If you see carefully, I can rewrite the same thing as F dot L. Can I do this?
L cos theta. Okay.
Okay. Now this is the work done which I have done on it. Okay. I had to calculate the dipole's energy. So it will be the negative of whatever I have done. Is that clear? Because the total energy is zero. Total energy, if I say initially it was zero, and I am doing some energy plus energy of the dipole. So what will be the energy of dipole? It will be negative of whatever I have done. Is that clear?
Okay.
So what is the energy of dipole? It is negative of F dot L. Make sense?
Yes.
Just put the values. What is F? F is nothing but Q E dot L. So P dot E. Understood?
Yes.
So this is the formula you have. Any
It's the
doubt?
same as torque.
Yeah, it is same as the torque. Okay. No, it is different. You can see the difference.
Negative. Yes.
No, no, not negative. The cross product or the dot
Oh,
product.
okay, okay, okay.
Now I'll just erase this part. Okay, let's not erase it. Again, I will take all those four cases, whatever three cases I took there. Positive, negative. Check this one. This is dipole, this is electric field. This is dipole, this is electric field. And this is dipole, this is electric field. Okay, just check it out. In this case, angle is 90 degree. Okay, uh, what is it? Minus P E cos theta. What is cos 90? Zero. In this case, energy will come out to be zero. Is that clear?
Zero. Yes.
Okay. No, no, it won't. It should not come out to be zero. Okay, let's leave it for now. Check this case. This one. You can see the both have a same angle. Is it?
Zero. Yes.
This is zero. It means what energy you will be having minus P. You can
Yes.
say it is minimum energy. Negative is meant to say bounded state. It is in the stable equilibrium side. Okay.
Okay.
Check this one. This is how much 180 degree. Cos 180 is negative. Mean to say negative, negative becomes positive. It has a positive energy. Clear?
Yes.
Mean to say it is a state of maximum energy. It is
Okay.
also some energy is there, okay, but we are not sure it is maximum or not. So we have maximum, then you will go to zero, then you will go where? Negative, the minimum state. Clear?
Yes.
So this is the thing. You can see just single formula, we can do all these things. Okay.
Okay.
If you want to get this derivation using the torque method, then how you can do? Let's see. That time, what equation I wrote? Torque into theta, is it?
Yes.
But this is not an absolute thing because we are not moving just a direct theta. Okay, we have to go in a by very very small steps. Small theta, then small theta, then small theta, because our force is varying by each cases. Okay, force is varying by each cases. Why I don't have to integrate here even though my force is varying by each step? Because this whatever the value of force I'm going to write, it is already derived. Okay, we have already derived by using the integration method. Is that clear?
Oh, yes.
Okay, so here what I'm going to do, I know what is dw. It is torque into d theta. Now I can integrate it out, and if you integrate this, you'll be getting w. What is torque we had that time? I just forget the value torque we had. Okay, the torque we had got was F dot L. I think this is what we got that time.
Okay.
Is it we got? I think this is what we got. I'm not sure actually. Okay, torque we already know the value, right? F P E sine theta, or you can say
Theta.
P E sine theta. Okay, if you integrate it out, this one, so what you will get? Cos theta,
Cos.
theta 1 to theta 2. Is that clear? In general, if
Yes.
you see, what we assume is theta 1 is 0. Mean to say, we are starting with this state. You can say because this is the zero energy state, so I can move from here to here, here to here. Although this is my negative state, so it will be preferable to go this side. Clear?
Yes.
But you have to remember that formula is in this. You can also add that Vd is equals to negative Pe cos theta 2 minus theta 1. Cos theta 1. Clear?
Yes.
This you can also remember. This is one more thing.
Okay.
So your work done will come out as how much? Pe cos the theta 2 minus cos theta 1. Okay. And in this
Yes.
case, again, if you see carefully, this is the work done by me. So what is the work done by this? It will be negative. All right. So if
Yes.
you ask me which formula you have to remember, the only formula you can remember these two, or either you can add theta 2 minus theta 1. This is these two you can remember. Okay. And
Okay.
and in derivation you can use any method you want. If you just simply remember force and length, you can go with that. Clear?
Okay, sir.
All right. So by this we have completed the first half of this chapter, which was based on a proper electrostatic. Now, like we have done the effect of electric field. Okay. Now we will be studying about the energy. This is the first
Okay.
discussion we have on the basis of energy for this chapter. In the next 7 lectures, we will be discussing more about what is potential energy, how it is stored in the objects, in different object, which kind of energy will be stored. And one more thing, I think the one of the most important part we have left is electric field due to the spherical shape. Understood this part? We
Okay.
have left this part right now, and I think I will teach this part when I will be teaching energy. What is it? Voltage inside the sphere. So first I will be teaching voltage inside electric field inside the sphere. Then I will move, at the same time I will teach you voltage also. Clear?
Yes.
All right. So this is all for the today's class.
Okay, sir. Thank you, sir.
Yeah. Goodbye. You can end the
Bye,
session.
sir.